All right, thank you very much, Nick. As Nick said, I really prepared this, for as a kind of opportunity for discussion with you guys. So really feel free, and we don't need to go to the old material either. So what I wanted to discuss with you is a topic which I find quite interesting, and I hope is going to be useful also for your work. I'm particularly targeting, the intersection between AI and science, but of course, more generally, equivalent machine learning can be used in a variety of applications. I'm going to focus here on the physics modeling a bit, but again, I hope this is not going to be a problem if you're not working on these applications, and you're going to benefit from more general exposure. So the idea of this talk is to start really with a tutorial. And at this point, I think it's really helpful if you interrupt me, if there's anything that maybe is confusing. Really, it's good to go through this slowly. And I will start, just discussing a little bit the idea of symmetry and what does it mean mathematically to have a symmetry in a problem. And then I will introduce the topic of equivariant neural networks, and in particular, discuss how convolutional and graph neural networks that you might have encountered before, right? They are really paradigmatic examples of equivariant neural networks. And finally, if time permits, I want to tell you a little bit about how we applied these ideas for a problem, as I said, in physics. Okay, so in this part, just starting slowly, right? So what is a symmetry? And you should really think about it as a set of transformation of some object that leave that object invariant. I like, the art of Escher, who is a Dutch painting that really somehow very eloquently describes symmetries in his work. And for example, this painting that you see here, actually it's a woodcut, I think, but it's called the Angels and Demons. As you can see, first of all, if you rotate this painting 120 degrees, right, it is exactly the same. So that's an example of a symmetry. This painting is invariant in the 120-degree rotation. Okay, there are actually other symmetries that one can talk about this painting, but that's fine. And what makes this powerful is that a lot of problems we encounter in nature are actually symmetric. You think about a flower, of course, is beautifully symmetric. Of animals, we are, for example, symmetric on the flip of right and left. To go to examples in materials where maybe a crystallographic structure which is symmetric. And in particle physics, also you have examples of symmetry, internal symmetries that really are key in understanding phenomena. And so let me just immediately switch gears and talk about mathematically what this means. So there's a lot of text, but I want to go through it slowly. So mathematically, a symmetry is described by what we call a group. So a group, you should think about it as a set of elements. And these elements are such that if you take two of them and you multiply them, you compose them. So there is a notion of composing symmetries or transformations, which is pretty clear, right? If your transformation is a rotation, composing two transformations just means rotate by the sum of the angles, for example, that you have in your two rotations. So the first axiom of a symmetry group is that if you take two symmetries and then you multiply them, you get another symmetries. And also for each element G of this group, there is an inverse symmetry. So something that takes you back to the original point, right? And we call this G inverse or G minus 1, such that if you multiply with G, you get identity I. Okay? So far, so good? Okay. I know it's a little bit formal, and I apologize for that, but I don't want somehow to lose people at this point, because I just introduced a little bit of formalities, because that's how we really can make the most of symmetries practically when you think about those machine learning. And I want you to have in mind that this example, which is an example of the group C3, which is a group of cyclic rotations of three elements, sorry, of order 3. Basically, you can imagine that there is an abstract element G, its square, and then when you take its cube, right, then we go back to the identity. So for example, if you thought about the 120 degrees rotation, right, this is actually in disguise the group C3, because if you rotate 3 times, 120 times 3 is 360. So it means basically same thing as no rotation, which is the identity. Okay? Good. And then when you think about symmetries, I mean, there is this concept of abstract symmetry, that is somehow what the symmetry group represents, and the concretization of these symmetries when they act on some object. And that's what we call the representation of the symmetry. So if you ever looked at, this equivariant neural network literature, that's all about these representations. And so what is a representation? It's simply a map, a row, that maps each element in your group to a transformation. And let's say that the output of this map, the space on which you act, we call it S. We have seen already the case when S was this angels and demons painting, right? And then we say that this group C3 is represented at the 120 degrees rotation of that plane, okay? Another example is the example of the output space being the three-dimensional vector, real vectors, R3. And then this group C3 acts as the following matrix, okay? And you see what happens here. This matrix acting on a generic vector V1, V2, V3 is simply cyclically permutes the entries of this vector, right? You see V1 goes to V3, V2 goes to V1, and V3 goes to V2, right? So that's a cyclic permutation of the entries of your vector. So that's a different action, and but it's still a valid action, because if you take this to the power 3, clearly, you get back to the original vector. So it acts as the identity matrix. We can also take this matrix, take the power 3, and you will realize it immediately. So that's the idea of representations, okay? You have an abstract group, which is, for example, this cyclic group of order 3, and then it can act, on the plane, on the three-dimensional vectors, and so on and so forth. Good. And then the last bit of terminology that I need is the notion of equivariance. So what does it mean? Well, equivariance simply means that your function, for example, between two sets S and S prime, or two vector spaces to be precise, commutes with the action of the symmetry, right? It means that if you first apply your symmetry transformation, you apply your action. It's the same thing as first applying your function and then apply the symmetry transformation. We will see plenty of examples of this in a moment, but that's the somehow mathematical definition of equivariance. So again, just to make sure we are on the same page, if you think about this action of the group C3, represented as 120-degree rotations, right? And if you think about acting on this triangle, right? You see what happens if you rotate it by 120 degrees, right? For example, this one becomes this one, so this triangle is equilateral. If you rotate another time, right, this becomes this, and then if you rotate 3 times, you get back to the original thing, right? So this means indeed, sorry, a lot of notifications here, but hopefully that's not going to distract you. And yes. Yeah, I didn't introduce it, sorry, but indeed, the idea is that F goes from some space S to S prime. So imagine that S, for example, could be the plane, R2, and S prime could be R3. Okay, then maybe it's worth writing it. So if you have F, it's a bit strange. Maybe I'll try another one. Ah, you know what? This is the one that requires paper, right?
It might have a whiteboard function too. Try it a bit.
Okay. Oh, this is good. Okay. You can see, right? Yeah. So let's take the example where this is F to R3, I said, right? Then this means that rho prime of G is equal to this three-dimensional matrix, for example, if G is C3, right? And instead, the rho of G is the 120-degree rotation, okay? Which I guess you can write it like cos 2 pi 120 degree is over 3, I guess. Sine 2 pi, so it's a rotation matrix on the plane, right? Minus sine 2 pi over 3, cosine 2 pi over 3. All clear to everyone? Okay. Yeah. So in general, the functions you want to model in machine learning will have this property, right? So, and most of the times, if you think about, for example, some classification problem, right, of an image classification problem, your input will be something that transforms maybe according to translation of the pixels and something like that, and your output is going to be invariant. So the output maybe is going to be just R, and then this row is going to be 1. It acts trivially. So that's a special case that is going to be relevant, and we're going to talk about it in a second. But is the mathematical framework clear to everyone? Okay, very good. Thank you. So, and indeed, let's switch gears now and talk about machine learning. So, as I mentioned before, maybe make our life simpler, let's think about the case when we have a function f, which is G invariant. Okay. And this could be, for example, I just made an example a second ago about an image classification problem, but more like a scientific kind of realm. We can think about the problem of classifying whether some configuration of a magnetic material, for example, is ordered or disordered. And this, at the human eye can be actually figured out pretty easily, because if things look more or less uniformly distributed, right, then this is a disordered configuration. If instead they look more or less uniformly distributed, then it is an ordered configuration. And then imagine the problem of writing a machine learning program that, given these pictures of these configurations, tells you, hey, this is a disordered material, this is an ordered material, okay? And then what you want to impose is that this function is going to be invariant if you translate, rotate, or flip your configurations, right? This shouldn't matter. And so that's the kind of thing that we say this function is going to be invariant under the group G, which is the group of these transformations of your space. Okay? So that's a typical problem that we're going to encounter. And I think it's a problem that you find also a lot in your applications, where you might know already that your function has some properties, and you should actually encode it in the machine learning model. Why should you? Because if you think about this cartoon here, which is the circle is the circle of all possible functions, okay? Then clearly, if you know already that you try to model a function that has this property, that rho of f is equal to f, that's going to be a subset of the space of all possible functions, right? So it means the search space, because think about the machine learning problem as a kind of optimization problem, right? Find the hypothesis in your hypothesis class, which explains better your data. So it's a kind of search problem. So if you know already that your function is in this corner of space, then you should better take your hypothesis class you're searching over, basically modeling only the symmetric functions. So say differently, the idea is that modeling symmetries or equivariance in machine learning allows you to have a lower sampling complexity. Okay, so you need fewer examples to learn this function, because simply the search space is smaller. It's of course a little bit of simplification, but intuitively that's why, right? And also it can reduce the runtime. Okay, first of all, the training algorithm, because it takes less than to get there, and also your model might just going to be smaller. Okay, for this reason. Okay, let's try to make this a little bit more concrete with an example. Okay, first I wanted to talk about this, again, the more general framework. So now that we understood that it is important to have symmetries in neural network, let's see how you do it in practice. So we consider, this feed-forward neural network, okay? And we call the number of neurons, or the dimensionality of the data at each hidden layer, N1, N2, N3, and 4. And then your neural network will have this form, right? W1, W2, W3, W4 are the weights, and sigma is the nonlinearity, for example. So how do you make this guy equivariant? Well, first of all, you need to understand how the symmetry acts. Remember, there was this idea of a representation, right? You need to tell me, for example, if it acts like this or like this. And so this means that we attach to each of the of these intermediate spaces, right, which are somehow r to the power ni, a representation, rho I, so an action of the group. So we need to understand how the group acts. And after you have done it, then you're more or less done, because then you just need to make sure that your W matrices commute with the symmetry rho of G, or they are equivariant. So you see, if you act, I guess here I screwed up the I and I plus 1, but you see the input should be I and this should be I plus 1. Okay, so we want that if you act with the symmetry, act with your weights, it's the same thing as acting with the weights and acting with the symmetry. So that's the basic constraint. And notice that this is a linear equation for the weights. If you do that, look at the bottom left, there is a symmetry G acting. This thing will go through, right? Because it commutes, right? It commutes through all these matrices. And if you imagine that it also commutes with sigma, which is something I don't want to enter right away, then this action, right, will go through, and then we guarantee that the output transforms in the right way. Yes?
Is this a sufficient but not necessary condition for equivariance? Because you're demanding equivariance at the layer level.
Okay. Very true, yeah, indeed. And there are other ways to enforce equivariance. I mean, there is a whole mathematical machinery which is called invariant theory, which basically tries to find a basis of the space of invariance. And so, you know, somehow I'm just saying this is what the machine learning literature typically does, because they have seen empirically this works. But you could also use other kind of ideas, and I'm happy to talk more about it later if there is interest. But this is one way. It's sufficient, not necessary condition. Think about it that way. So let's try to be a little bit more concrete and go through an example together of how does this work. And here I have our example. Again, I want to think about the case where my group is this C3. Remember, right? It's this cyclic group of order 3. It somehow describes the symmetries, right, of the triangle. And let's imagine that we just look at one layer, okay, W, and that's our linear layer. And the input space is three-dimensional. The output space is three-dimensional. And now we ask ourselves, can we write an equivariant layer under this group? If we assume that the input and output representations are given by what we saw before, namely this matrix. Okay, so the group cyclically permutes the entries of a three-dimensional vector in the input. It cyclically permutes the entries of the three-dimensional vector at the output. And basically, we want to solve the equation that is, if you see the definition of tau, right? What you want to solve is this equation. You want to solve for W, the equation tau, W, time minus 1 equal to W, okay? Or you can put it the other side, tau is invertible. And so only the W's that satisfy this equation, right, will be equivariant. And so the question is, okay, how do we construct those? Well, you could see, okay, this is a linear equation for W. You can use your numerical linear algebra package and find the solutions for this. Fair enough, that's one approach. Otherwise, in this specific example, it's actually easy to know what is the solution. And I just, somehow tell you without necessarily proving, but I want to make you understand why is this the case. First of all, notice that trivially, if you take W to be tau to the power I, this is true, because tau to the power I, which is the ith power of the matrix, commutes with tau itself. And then, since this equation is linear, also, it will be true if W is equal to a linear combinations of powers of tau, right? There will be a case where you have A times tau, B plus tau square, B times tau square, and C times tau cube is equal to I. So what we have just shown is that this matrix, which is called the circulant matrix, okay, is actually equivariant under C3. Clear to everyone? Okay, good. And the interesting thing is that this is all there is. And in fact, you can easily show then that this is a good dimensional reduction of your problem, because initially, if you have a dense 3 by 3 matrix, you have 9 parameters, right? But then if you impose this actually condition, you end up here, and so you have 3 parameters. So this is what I meant before, right? That this is somehow helping learning, because now instead of finding 9 parameters, you only have to find 3. And so this will require fewer examples to learn. And also, in the case of, for example, convolutions, right, as we'll see in a second, is also going to be allow us to reduce the runtime. Okay, so this is the kind of computations you need to do if you want to implement your equivariant neural network. You know your problem has a certain symmetry, for example, cyclic permutation, right, for whatever reason. You need to solve this equation, and basically that's it. And now these are 3 parameters. It's up to you, to find the values of them. Okay. Naturally, if you take complicated groups, these things become complicated, but it's more like then an algebraic exercise, a combinatorial exercise, more than really a conceptual difference. It's going to be always the same kind of idea. Yeah, of course.
Why don't we use a higher order?
Yes, this is a good question, because tau to the power 3 is equal to identity. Is it obvious, or shall I do it? You see it, right? Because tau, remember, permutes cyclically. So maybe let me just make sure this is clear to everyone. So I just do V1, V2, V3. Sorry, it's low. So if you do this, you remember what happens is that the 1 goes to 2, the 2 goes to 3, and the 3 goes to 1, okay? And now let's do it again. Then if you do tau squared, you see what happens. I'm gonna apply, then this goes to here, then yes, this goes to here, and this goes to here. Am I doing it right? No, sorry, it's the other way around. Anyway.
The second one you have the.
Yeah, so I need to basically. Yeah.
That's wrong.
Yeah, so this is wrong. Yeah, exactly.
Yeah.
So 1 goes to 2, sorry, and 3 goes up here, and then again, right? 3 goes here, and then 1 goes down, and 2 goes up. And then if you do again, right, then 2 goes here, 1 goes here, 3 goes here, which is exactly what we said. Okay, good. So we have proven that indeed we cannot put more. Good. Okay, any other questions? Yeah.
So is this the symmetry applies to both the input?
Yes.
So if, for example, in 3-dimensional, it would X, Y, Z changed, and
yeah,
if the output was 2-dimensional, it would try to do it.
Yes. Yes, indeed. And in fact, I mean, you're hinting somehow at something that is a bit more complicated. But in practice, there is some, theory basically of group representations, which tells you that you can always reduce any representation in terms of you study physics, I guess, right? So probably you heard about these irreducible representations, right? So in general, you can if you have a representation which is the sum of irreducible, what happens is that you can only have non-zero elements between irreducibles that are of the same type. So if you have 3 and 2, it will be completely zero matrix. There is no invariant, basically. So anyway, but this was so in general, if your input is 2-dimensional, you would like to have an intermediate layer which somehow contains that 2-dimensional representation in some way. Yes. Otherwise, there's no non-trivial map. Yeah.
Is tau predefined?
Yes.
Prior.
Exactly. So basically, the idea here is really that we know how the symmetry acts on the input. We know how it acts on the outputs because this is some problem given, and we can choose how it acts on the intermediate layers. So here we know that it acts on the input as tau, and we choose that it acts in the intermediate layer also as tau. We could take other things like also this question. Yeah.
What if we don't know act on our space?
Yes, actually, this is a very interesting problem. To be honest, it is a hard problem, so I don't think it has been solved at all. But there are ways to, especially in dynamical systems, right? When you know that the symmetry has a certain somehow structure, there are ways to learn them. Yeah, it's a very interesting actually concept, and it's related also to this disentangled representations. You know, there is actually quite a lot of literature. But I don't think it has been any way solved, and so it's quite open, yeah, how to go about if you don't know. Also, the problem of approximate symmetry, of course, could be relevant in practice, and this is not necessarily tackling this. Okay, so I just want now to move to examples that you should be familiar with, I think, and maybe let me, for this one, move this guy here. Let's see, maybe here.
Can I just ask a question about that last framework?
Yeah.
So that makes sense if you've got a finite number of symmetries, but if you have continuous symmetry, then can you use?
Yeah, so you're thinking about, for example, a Lie group symmetry, right? Like a SO3, the rotations of the dimensional space. Yeah. So this indeed is like a, some kind of discretized version, right? This clock symmetry. In that case, what you do is that you cannot possibly check the, impose the condition for all the elements of a group because you have an infinite number of them. However, in all the cases, you can always find a set of generators of this group, right? Exactly. So basically, you know that you can write a genetic group element, right, in terms of a product of some generator, power of some generators. And then if you can impose the equivariance condition for all the generators, then you're good because any group element then will be equivariant. So that's how we do it. Yeah. For example, for SO3 will be rotation around the X, the Y, and the Z direction. Yeah. If you just impose these three, then the magnetic rotation will also work.
Yeah. A rotation around X could also be continuous as well.
Yes, but it's always of the form, power of that rotation. So if you think about, is it clear what I'm saying?
So.
Yeah, so basically you need to think about a way to write your group element as a product of generators. And typically this involves powers of the generators, right? So then if it holds for the generator, say G1, it also for G1 to the power K, for example, because, right, basically, it's rotating, by the rotation k is equal to rotating k times by the rotation 1, right? So if it holds for the rotation of 1, then if you do it k times, it's still there. It's basically how the math somehow of this equation works if you compose, many actions. Yeah, we can go through it if it isn't clear. Yeah.
So I guess it's another sort of technical question, but this is like a simple abelian group.
That's right.
So therefore, you've got tau and it just keeps on operating. So does this actually work at all for non-abelian groups? Or do you
yes, it's similar to this question. Basically, in non-abelian groups, you can also come up with a set of generators. Okay. Like if you think about SO3 we were talking, right? Mm-hmm. So in that case, you can impose it for the generators and then it will hold for the most general group element. Because they will all act trivially, right? Even if they don't commute, it doesn't matter. They will all act as identity somehow. Yeah. We can go through some maybe more detail for the Lie algebra, the group if you want, because that's a bit more technical. Yeah. Okay. I mean, I'm just saying that I do not want maybe to take too much time here, but it's a very good question. Yeah. Okay, good. And so let's just go to the convolutional neural networks, right? So in this case, the symmetry is what I write here as CH times CW. So remember, C3 was the cyclic group of order 3, okay? Now CH is the cyclic group of order H, where H is corresponding to the height of the image, as W is the width of the image. This means that the symmetry we want to capture is a translation of all the pixels, right, either in the horizontal or in the vertical direction. And that shouldn't matter for an image classification problem. Okay, so if you have, for example, your input is this lizard here, right? It doesn't matter if your lizard is in the bottom left corner or the top right corner. We always classify it as a lizard. That's the idea of convolutional neural networks. And so mathematically, what we said before corresponds to taking the group as the product of these two groups, two abelian groups indeed, And then the input and output are taken again to be the same representation in these specific examples. And then the property of the convolution is that it somehow satisfies this commutative diagram. If you start from this image, you apply convolution, so you get this blurred image, and then you translate. It's the same thing as first translating and apply the convolution. Okay, so that's really pictorially what happens with this conditions, analog condition of what we wrote before, right? It's really the commutation of these operations. And so that's what you actually do when you think about the convolution. Was this familiar to everyone, I guess, more or less? But it's part of a more general framework, and that's the point I'm trying to make here, okay? And then basically the graph neural network, that's also quite popular architecture. It may be, less familiar, but it's also quite relevant, for example, when you think about the molecules, right? It's an example, but there are, of course, social networks. I mean, there are lots of things that can be thought as graph naturally. And so here you see that, you have a molecule you can associate to each atom a node, and to each of these bonds, an edge in your graph. So naturally you can think about it as a graph. And one property that you want to impose is that the prediction should be independent of how you label your vertices. If I say this is my vertex 1 and this is my vertex 2, it shouldn't matter for the prediction whether I label this 1 and 2 or 2 and 1, right? Basically, it's a natural kind of a property that comes about just because you decide to label them, right? To put in your computer, this is element 1, this is element 2, but you could definitely be able to relabel vertices and should get the same prediction. So what we want is that the graph convolution, which is somehow the primitive of graph convolution neural network, needs to be equivariant under permutations of these labels. That's the idea. And so if you have looked a little bit about these things, you probably know the notion of graph convolution, which generalizes the convolution we just saw before. And the idea is that you do message passing, okay? So suppose that you need to think about that you have some vertex features, which I call xi, right? X's. And then you have a linear layer W, which produces an output feature, x prime. And so message passing means that the feature x prime at vertex I is going to be obtained by collecting the messages from its neighbors. Okay, so here what the formula says is that take a matrix D, you multiply by a sum over J of the adjacency matrix of your graph. Adjacency matrix of your graph, right, is 0 if the vertices are disconnected and 1 if they are connected. It can also be weights or something. But this somehow implements for you the sum over the neighbors, okay? And so here the neighbors of the vertex I are, for example, these 3. In practice, you also wanted to have some self-loop, but okay, it's maybe a small detail. But clearly, this is invariant under permutations, because you see, if you now relabel your vertices, clearly the output is going to be relabeled correctly. And so far, so good. Okay, so these are all examples somehow that allow you to understand why these ideas of equivariance have been actually influential. And in fact, this is actually the conclusion of the tutorial part. So if you have more questions, it's a good time if you want to ask more. Otherwise, I can jump to the more research part. Yeah.
I haven't come across.
Okay, very good.
You say like commute the operations.
Yes.
Is it exactly the same as that?
Yes.
So all linear operations would.
I didn't understand. Sorry. Can you say it? I didn't get it.
Yeah.
Equivariance means maybe yes, exactly. So equivariance means that, for example, this holds, right? Maybe the more general one. This holds. Good. So
then if all linear things
are equivariant,
you don't have an activation there that do anything to you.
Yes, and the idea, you guys, exactly pointing out what happens with the sigma. Good question. So I guess there are two cases. Case number one, your symmetry acts as a permutation of the entries of your vector. In that case, you're good. You don't need to worry about sigma because sigma acts entry-wise, right? So it naturally commutes with any permutation of your entries. And this is actually the case for what we saw before, translations, You know, even flips of your image, rotations of your image, these are all like permutations of the entries of your image, right? So basically in that case, it's good because any pointwise nonlinearity is going to be good. It's going to guarantee that the whole thing is equivariant. However, maybe in the case also we were discussing before with the non-abelian groups and rotation groups, it might happen that this is not the case, and then you need to think about how do I make my nonlinearity equivariant? And that's actually complicated. So there are some ideas, but it's a little bit technical. And that's, I think, one of the drawbacks of this approach, rather than maybe what Nick was saying, maybe, you know, do something else, maybe with some invariant basis or something like that. Yeah.
Sorry, in this equation, is G the same thing as F? F is equivariant if, but I don't see the F in the equation. Is G F? The mapping from layer to layer that we're
Okay, so sorry, maybe the notation is a bit confusing. F of X is our neural network. Yeah. X is the input, good. And then we call G an element of the group, okay? So for example, G could be this three-dimensional matrix tau, okay? So maybe let me just unpack this a little bit. So just, you know, consider a very simple neural network that is 2 layers, and it has maybe 3 neurons like this, and maybe 3 as well. And then we have matrices W1 and W2, okay? So then this is our F, computes this guy. And then what I'm saying here is that tau W1 is equal to W1 tau, or Wi, say, for I equal 1 to 2. So this is rho of G. Okay? Okay, sorry, the notation maybe is confusing, but it's that's what that is. Okay. And yes, of course.
It's just on the title of the paper that was on the last slide.
Which one? This one?
On the last slide that you showed. The graphs, yeah. It's like invariance and equivariance.
So this is a very good paper, actually.
So what's the difference between invariance and equivariance?
Yes.
In terms of neural networks?
So invariance is a special case of equivariance. So yeah, sorry, I didn't display it. This is a good question. Let me just maybe remove this and say it once more here. So we define a function equivariant, right? As we said in the example before, there was this function f from s to s prime. And this is equivariant if rho of g f is equal to rho of g prime f, okay? It's a bit abstract how I'm writing it, but is it clear what's going on? Yeah. So here you act on the input to the function, and here you act on the output to the function. This is equivariance. Invariance means that the rho prime of G is equal to 1. So in that notation, is that this representation is trivial. It's a singlet representation. Okay, so this is just a special case. Okay. Yeah.
Yes, just for a primitive physicist like myself, like I always remember that energy is invariant.
That's right.
And forces are equivariant. Right. So they should transform with energy just the same number no matter.
No, okay. Right, yeah.
So
thank you. Yeah, this is a very good intuition to have in mind. Yeah. Okay, good. So I don't know. We have 15 minutes. Should I press on or shall I stop?
I mean, you had a fair amount of questions during, so I thought maybe you should, you know, be briskish. But
yeah. So I actually have a sketchy thing, and I realize it might be more useful for people. It's coming. I'm using this, AI designer in PowerPoint, so it's pretty cool. Okay, so this is like a paper that we somehow wrote, and it's a little bit more, in depth in some specific application, but I hope maybe there is some aspect that can be more generally useful. That's why I'm going through it now. So what is the problem statement? Actually, problem statement indeed is a general problem, which is the problem of sampling. Okay, so you might have encountered in your scientific applications, terms like Markov chain Monte Carlo, right? So this is like quite useful when you need to indeed sample from some probability distribution, a high-dimensional probability distribution. So in physics in particular, we typically consider this kind of models, which we call lattice models, where you have a graph, here just a square lattice, and then you have some variables that live on the graph, which I call phi. Okay, so x is a vertex and phi of x is a variable that lives on the vertex. And then we have an energy, which I call h, which is given a phi, you can compute this function, which tells you the energy of the configuration phi. These kind of things also are ubiquitous in machine learning, right? If you have seen probabilistic graphical models or this kind of thing, right? This is all part of the same kind of ideas, that you define a statistical model on a graph. And so this prescribes how the variables interact. Good. And so this is actually quite relevant in many areas of physics. For example, material science, high energy physics. You typically do want to solve the problem, which is how do I sample this probability distribution? Okay. And because sampling this probability distribution, allows you to compute observables. Then you can compare with experiments and so on. The standard in statistics is called the Markov chain Monte Carlo. And here the idea is the following. If you want to compute the sum over phi of f of phi times p of phi, you can discretize, you can sample the summons here, right? And how do you sample? You create a Markov chain. So let's do an example concrete. You have probability distribution on the plane, which is, say, non-zero only on this blurry somehow area here, okay? This thick region. And naturally, if you start to sample uniformly in the plane, you're going to pick a lot of points that are, wherever in this plane, and at which this p is going to be zero. So that's going to be very wasteful. What you can do instead is to create a process, a stochastic process, which is a Markov chain, that somehow visits these high probability regions, right? And that's what you see here with these arrows. So there are ways to do it. The problem is that the samples you get are correlated, right? And this correlation can be detrimental because, if you have samples that are very similar, it's a little bit wasteful, right? Basically, you need to sample a lot of samples to get, a good representation of your space. So that's one problem. Another problem is that you actually need to tell me what do I do in practice. This is called the transition matrix. You need to handcraft it, and every different problem, right, will require a different transition matrix. So that's quite difficult also to come up with good answers. And also, for these reasons, it becomes very computationally intensive. If you think about actually high energy physics like lattice QCD kind of applications, this is going to be really not necessarily the bulk, but close to the bulk of the supercomputer time, together with DFT maybe. So these are really the things that we do want to improve on, because these are things that people really spend a lot of compute on. And that's somehow the motivation. But as I said, perhaps even apart from the physics somehow application, this is a general problem that you might have encountered, problem of sampling. And so how can we solve it using machine learning? So the idea is actually pretty naive. Try to learn a map, a function that maps a Gaussian, which is an easy to sample distribution, to your target distribution. Okay? And so I call this map here f, little f. So this map little f is parametric. It depends on parameters theta. And we'll map this Gaussian random variable z to this random variable phi in such a way that z is Gaussian and phi is distributed according to the target distribution p. Let's imagine now the space of probability distributions as this sphere, right? This gray sphere. The Gaussian sits here and our target sits here. What happens if you take a random neural network, you pass through your sample Z to the random neural network, you end up in another, this basically output of the neural network will be distributed according to some other distribution, which is somehow this other one here, which of course will in principle not have anything to do with your target. And now the idea is the following. Well, let's take a loss function, which is the distance between these two distributions. And now we try to find the values of the parameters theta such that this distance is minimized. Because that's the idea. It's quite naive, as I said. But so let's see how we can do it. Is the somehow idea clear? Okay, good. So what we did in our paper is not necessarily the only approach, but there are some reasons to do this that I will come to, in particular respect to equivariance, is to use this technique called continuous normalizing flows. Of course, we could do another tutorial on this, but in a very nutshell, the idea is that you define this map as the solution to an ODE. Okay? So the ODE is the following: psi dot equal to g psi t theta. So theta are the learnable parameters, t is time, and psi is your variables. And let's declare that at time 0, psi at time 0 is equal to z, which is a Gaussian. And then we want that psi at time 1 is equal to phi, which is our thing. How does this work? You can see on the left. This is your target distribution, for example, this bimodal distribution. You start from a Gaussian, and you see as time progresses, actually the samples and the log probability, the probability distribution, really start to resemble the right thing. So it starts, it's like a blob, a Gaussian blob, and then with time, these things get pushed apart so that you get the right thing. Okay, I know I'm going very fast, but just to introduce a little bit of the background, then of course we can discuss more. So the idea again is that you have the parameters theta and you want to learn them. Okay. So now we come somehow to our contribution. So our contribution is to come up with the parameterization for this G. Okay, so we use this prescription and we find the G which has the right symmetries, the equivariance property, because this is now a learnable function. So the way we do it is a little bit maybe different from a standard neural network, because what we do is that we start from this vector phi1 to phi n, so our input configuration. Then we produce some Fourier features. So here, that's another interesting concept in machine learning, that sometimes you can use some Fourier features to approximate a function. And this actually is a similar idea we use here. And then in this feature space, you can just act linearly with the linear layer W. And then the only thing we need to do is to impose that this W is equivariant. So it satisfies this property for the symmetries of the square lattice. And what are the symmetries of the square lattice? You have these two cycles, which are the translations in one direction and in the other direction. And then you have this group, which is called the dihedral group, which is the group of 90 degrees rotation and flips. This is very schematic and fast, but just to give you an idea that with the right parameterization, you can actually solve this problem. And we solve it pretty straightforwardly, because then it becomes like, just a single layer of a convolutional neural network, which is equivariant under rotations and flips. And in fact, we do something a little bit more, that by using this learned model, we can also learn across parameter space. So now think about the sampler. You need to sample for each values of the couplings in your Hamiltonian, your energy. And in this case, what we do is that we somehow have our neural network be knowledgeable about this coupling, so that at deployment time, we don't need to retrain it for a new coupling. We have already seen a lot of coupling, so we can extrapolate to a new coupling. And we also show how this can be transferred across lattice sizes. If you can train maybe for 10 by 10 lattices, this is going to be a very good initialization for 12 by 12 or so and so. So there are a lot of tricks you can actually play once you enter this learning paradigm to sampling. And just to give an impression here of what's going on, so we just do some benchmarking, and we find a very good improvement of this equivariant architecture with respect to the previous model, which was not equivariant. I'm not, expecting you to somehow understand what's going on here, but what is plotted here is the measure of the independence of the samples. So the higher, the better. And for a lattice which is 64 by 64, we find somehow this kind of value, while the previous state of the art was basically 0. So they couldn't really do it. So this was a big boost. And on the right, if you're more needed from a physics, chemistry background, this is like a way to identify a phase transition. as I said, you can condition your neural network on parameter space so you can, find phase transitions, which is an interesting application for this thing. And this brings me to the end. So I wanted to make a case that, symmetries are important, equivariance is important, it allows you to reduce sample complexity at runtime. And I mean, also personally, I find it a very interesting topic. It's like intellectually, of course, it's an interesting topic. And so we show that the convolutional and graph neural networks are equivariant. So you can understand now why do they work and maybe how to generalize them. And also, specifically, these methods are quite useful when you apply to a physics problem, because they typically are quite symmetric, and so you can leverage these symmetries to make it work better. Okay, that's it. Thank you. Thank you very much.